I will. I just started the stream. So I'll tell everybody. There's good news. This is the last class you'll have for me this semester because next week is canceled. Oh, I know. I'll miss you too. I wish I could be here. I'm just unfortunate. I've been called into something in a different city and I won't be back in time. Probably couldn't get out of it. And so I thought, nobody's going to complain. Wait, are you going to complain? They lodge a formal complaint? That'd be fine. That'd make the little ego inside go, oh, they like me. Anyway, no, it's not a popularity contest. Let's see here. I don't know what contest is. I wanted to show you something first. In lieu of me having all these classes I missed last week, I really wanted to be here, but I took a $115 lift from Manhattan to LaGuardia through rain and whatever else, only to have my plane canceled, and decided I'd just book the $180 hotel by the airport because they couldn't get back that day. Yeah, you know how it goes. Anyone else go to AERA last? Yeah, how did it go for you? You didn't have any problems getting out?
I left the day after.
Nah. Way to go. You guys know how to do it. I'm like, no, this is going to be cool. I'm just going to go for the weekend. I'll leave Monday morning. It'll be plenty of time if there's a plane that gets canceled or whatever. No. So yeah, it was pretty bad. We were going through some puddles. I didn't know that we'd make it through. Let's just put it that way. So in lieu of me not being here next week, I've switched the website around, and I have lectures up that I gave to previous classes. By the way, I love you guys way better than them. So, not the same atmosphere, not the same people, probably some of the same jokes, bad ones. But if you're really wanting to enjoy multivariate, I've got some cool things up. I've got missing data. Ironically, missing data is what we'll be missing next week. Sorry, bad joke. Thank you, Ahmed. Thank you. At least one of you. At least one of you. Then if you really want to know why all of my colleagues in REMS are wrong, you can watch the PCA and EFA. I said that. They're wrong. Some of you inciting fights between us. Anybody? No, I'm just kidding. But they are wrong. I'm not kidding about the fights, but not kidding about them wrong, but probably not fights anyway. And then I put some classification stuff up that's not really that good. But do watch the PCA and EFA one if you watch nothing else. That's kind of fun. It's a terrible idea. Actually, I'll just stop there. Today's Bayes, though. Are you excited about Bayes? All right. This is the moment you've all been waiting for. Bayes. And right now, according to people in the world, Bayes fixes everything. I don't know if you know that, but that's sort of the way Bayes is viewed by some people in the world. To do this, before we get there, I'm going to give you some lecture material, and then we're going to have an example in R. If you'd like to follow along in R, you have to go to this link on my website. It's from a program. It's a program called JAGS, which stands for Just Another Gibbs Sampler. And you can download it and install it. It should install pretty easily regardless of whether you're on Mac or Windows. But that's the main thing that you have to run this. If you don't care, then don't do it. No problem. It's free, though, so you get what you pay for, just like R. In the meantime, if you're doing that, one thing I wanted to remind you of is that as of yesterday, I believe, you could go and do us all a favor and rate the class online, provide your opinion. Under your Blackboard page, you should see a My Course evaluation for this course. It should be open. If you're sitting there with your computer in class right now, please go ahead and rate it. Right now, 11 of you in one day have replied. That's awesome. But I'd love to hear from more of you. It's not as easy that I can just figure out who did it. Otherwise, I'd give extra credit for it too. All right? Seriously, I would. But yeah, please go on there and rate the class. We've been doing online ratings for this is our third semester doing this in my department. And yeah, the proportion of people who are doing that are very low. So I'm supposed to set aside class time. Well, I can't see what you're rating, right? If you want me to leave the room, I guess I could. Or do this over break today, I'll leave the room. Something like that. Do you need me to leave the room, or do you want, I mean, I'm not looking over your shoulder. It's anonymous, I promise. Look, I can't even tell who's on there, right? This is what I see right here, response rate. So do everything you can. And certainly all of those people watching on YouTube, I won't be able to see it. So good, bad, or ugly. Tell me what you think. There's some questions at the end that have kind of the open-ended prompts. I really value that feedback. I do try to, as I told you at the beginning of this semester, this class is sort of it is an experiment in how to do this. And yeah, I didn't get it right all the time. I hope I got it right enough to give you something that would make sense and walk out of here with more knowledge than you came in. But more feedback helps me get it right for the next set of students. Or you could be like, screw them, man. Forget it. What else? Any questions, comments? So there's no quiz next week? No, nothing. In Blackboard, now we had some issues with Blackboard grades. I think I've fixed most of them. So if you go into your grades in Blackboard, I'm not going to do it because I don't want to show you everybody else's grade. But if you go in there, you should see 15 quizzes. We took maybe, what, 6 or 7 of them? The rest of them got all extra credit points. All right? You should see 8 homeworks, with the exception of homework 5, which you're currently working on. Homework 6, 7, 8 got 9 points each. Okay? So I gave you like lots of points because I just wanted to keep the scale the same. So what you see in there in your grade in Blackboard should be close enough to accurate to what would happen in the class. So when you finish this week's homework before the end of day on Monday of next week, that's a 9-point assignment. You take those points that you'd get from that, add it to your total right now, and that's the number that you get for the class. And if you want to know how that translates into a grade, you can go to the syllabus, which is right here on the course materials site, and there is a grade scale right here. Basically, if you're looking for a straight A, of just an A without an A minus or something attached, 93 points or above. I think, the B range is 80 or above, B minus and whatnot. So I think mostly all of you are going to be getting probably close to an A, B, somewhere around there. So I don't think anyone's in danger of anything, but if you want to check up to the minute as of right now, check your grade. Of course, if there's any inaccuracies, let me know. I will say if there's an inaccuracy and you're already close to above 93, probably less of a priority to me. I'll apologize, but fixing it will be a little bit harder. You know what I'm saying? Like if you got an A, I believe you, you're right, I trust you. You're not getting an A minus, that's for sure. And there is no prize for top point getter in the class because FERPA won't let us do that. I'm just kidding. Sorry. Can you imagine if classes did that? That would be terrible, wouldn't it? Anyway. Oh, that's a bad idea. So, everybody looking right now, does it seem to be appropriate? If there are any, I've had some issues, clearly some issues in technology this year. I'm furiously looking for a way to change the way the online homework system is. I have a hope that I might be able to hijack Blackboard to do it for me. Like if I can use R to create a bunch of essentially test forms and then upload them. I saw someone do this in R before, just recently, so I'm hoping that I can fix that before the next time. And then we won't have as many snafus, hopefully. I still will get the R file wrong, but at least the grading will be consistent, right? I'm trying to minimize the sources of error where this goes. So, any thoughts or questions on all of that? Yes, Ryan.
Still have 100, right?
What?
Still have 100.
Yeah, 100, technically speaking, we had up to 107 points you could get in class this year. So 7 were bonus on top of the already however many quizzes I gave you for free and then homeworks. You can see I don't care. I mean, like, honestly, I don't care about your grade. I want you to do well. I want you to learn the material, right? Sort of trying to be my own way I wish people were in grad school for me. It's like the grade is the motivator sometimes. I'm okay to reach you there. I want to give you that motivation, but I also want to try to make it where it's also the grade is a great fear, particularly in this class when you can't get R to work. All right. Any thoughts or other questions? Bless you. Okay. No thoughts, no questions. I think I covered everything I need. Once again, no class next week. No class next week. No class next week. You have like an early out from this class. There's nothing else to do. You can sit back, apart from the homework. Okay, can I give you a funny story about me again? Because I like to brag about how right I am about some things. This is me this morning, right? I'm like, I need to give you guys your grades for homework 5. Because I've got all the other grades in there, and you'll need that. So I went and pulled down the homework, and I opened it up, and I'm like, next to nobody's completed this. What? Did I drop the ball? Like, did everybody think, like, oh yeah, idiot, it's due next week. So, yes, I don't have your homework 5 grades there. They'll be put up next Tuesday. And they, of course, again, you can always submit it late, and there's a penalty. Technically speaking, if you've missed any of the homeworks throughout the class, there's that 4-point penalty, which honestly shouldn't be that big of a deal with all the extra points everybody's gotten. The other part of that is you can submit your homework up until the end of the semester, the day of the end of finals week, if you've anything late with the late penalty. That make sense? All right, cool. Cool, okay, and of course, anything else, any problems with grades, anything that you see, please do email me. I'm happy to help. It's probably something I did. Okay? But EFA, I'm right about. Uh-oh, Ryan's not picking a fight on this one. Did I touch a nerve? Is that the problem? Uh-oh. Never mind. Food in the mouth. Should we do Bayes? Let's do this. Okay, Bayesian statistics and Markov chain Monte Carlo estimation. I separate the two. They're not necessarily the same. I will say anything that's a Markov chain Monte Carlo, or MCMC as we call it in our world, uses Bayes. So therefore, Bayesian is sort of nested. Every MCMC program uses Bayesian statistics. But not everything that you do in the world has to be MCMC. And you can do some Bayesian statistics outside of MCMC. So that's sort of where that goes. So this is essentially how we step forward. What it is, what it does, and why people use it is Bayesian statistics. And we're going to try to use MCMC a little bit today as well. So let's do this. The Bayesian statistics, or Bayesian statistical analysis, refers to the use of some type of models where at least some, but usually all of the parameters of the model are treated as random components. You haven't seen many random components this year. In the video that didn't, the lecture video online there where the audio didn't come through very well, I sort of talked a little bit about random intercepts, but I didn't get into them too much. Basically, what we're saying is, if you think of a linear statistical model, we had all our betas in it. Those betas have some type of distribution they come from. And you're probably thinking to yourself, well, wait a minute. The betas that we have, when we do LM or we do GLM or whatever, the NLME or all those letters that don't make any sense in R, they have a p-value, so there's got to be a distribution. Are you thinking that? Maybe? So the difference between Bayesian statistics distribution and the distribution that you get with that p-value that comes from NLME or whatever package you're using, it's not Bayesian, is that the p-values in the non-Bayesian case come from several of the results in statistics that we sort of believe that are true, such as the central limit theorem and the theorem called Slutsky's theorem. Basically, it's how those parameters would behave if you had repeated experiments with a certain sample size. And so that is what we call asymptotics, what we call kind of limiting distributions. These are why we see p-values. It's why we see a z-statistic or a Wald test. We call it normal. It's because when we use the likelihood, like a maximum likelihood estimator, we saw that the distribution of the parameters converges to a normal distribution as n gets big, right? And so it's sort of a consequence of nature that we had a p-value with everything, right? I call it nature, but it's sort of one of the laws of the universe, right? The central limit theorem, it's just one of the things that we do, actually. It's not just that. It's several different theorems put together to give you this result. In Bayesian statistics, we try to say, no. Bayesian statistics are also subject to those laws of the universe, of the central limit theorem and Slutsky's theorem, I think is what it's called. Some of the other issues that show up, work with Rao and so forth. They still have to deal with asymptotics, so as n gets really, really big, Bayesian statistics work the same as maximum likelihood. But in the interim, what we're going to do is assume each parameter follows a distribution. Right? So we're going to say, hey, there's each of our betas, they come from a normal distribution, let's say. And that's where the difference lies. We assign a distribution to them. We end up getting the distribution we assign to them is something we call the prior distribution. So it reflects our belief where the parameter should be. And if you're like me, this is my criticism of Bayes people, they think, oh, it's prior, you can put prior belief in. And I go, okay, do it. I've got this linear model exercise for you for homework. Tell me what the beta should be between these two groups. Hard to do, right? How would you figure that out? Well, let's just assume that you could. Or better yet, there's other ways. The way I look at it is sort of an agnostic point of view. Like the prior distribution is one where you just say, I'm going to do as least amount of harm as possible. So if I have a beta, like an intercept, I might say, oh yeah, the intercept has, I think that intercept, if I were to do this experiment over and over again, that thing follows a normal distribution. Okay, great, that sounds good. What's the mean of it? I'll say 0. That seems a pretty bold statement, but let's say what's the variance of that normal distribution? 300,000, right? So basically I allow it to be this really big normal distribution. What that effectively does, it says I'm putting very little weight to any one of those numbers that could possibly be there in my prior, right? So it's an odd concept to think about. Now, for instance, may I use you as an example, Sammy? Sammy over here has small samples and some very rare occurrence things that you study. So you not only have small samples, you also have even smaller sets of people that may have problems that we did. And these people may be very well studied, let's say. And say maybe you're trying to replicate a study that happened 10 years ago as part of, the initial part of your dissertation. What you can say is, okay, well, I have a better guess now. Instead of saying, I'm going to put a prior on my parameters that essentially says I have no information, a very, very broad prior like that normal I talked about. You might say, well, in this study, they found that the difference between these two groups was 5. I'm picking the numbers. So you set the prior mean to 5. And you say, maybe, okay, the variance of that mean might have been this much in that study. So you might even just use that directly. Okay, here's the prior variance. And what that does is it informs the analysis such that in Bayes, that sort of sets the kind of the entry point of what that parameter might be. In fact, if you collected no new data, you effectively get the same result as the study from before. That's the result, right? This is your prior information. But the next part of the Bayesian analysis comes from a distribution that is given by the model itself. Right? So everything we talked about with the linear model, the distribution of y given x, right? We use that density. The same thing that we form a likelihood function with, that's still there as part of the prior, as part of the analysis in the Bayesian world. So we get some information that comes from the data in the model, and some information that comes from a prior. We put them together, and the result of that is something we call a posterior distribution. With me so far? Kind of weird, lots of terms. There's lots of vocab. Bayes is like, it's like speaking a completely different, if all this class was a different language to begin with, Bayes is like yet another version of that language. Right? I know. So, prior distribution, your belief, right? How strongly you believe what the parameter should be. Like, if we were both doing this study, if Sammy is well versed in her field, she's like, well, I'm going to put the belief that happened based on the previous research I saw. If I'm new to Sammy's field or I'm not trying to do that, I might say, well, I have no idea. My belief could be much broader. So you see the difference. Like your prior distribution would be very peaked around that difference of 5, where mine might be very broad. It still might be centered at 5, but very broad. Then we collect the data, we put them in a model like we do now, and we build a linear model for it. And the result of that linear model is sort of the answer, or what we call the answer. It's what we would get in the summary statement in R. Right? We have the output, the results. But those results reflect a blend of your prior belief and then what happened with the data. Right? So it's like prior belief and model. Whereas right now, and when we do with our analysis, we have it a little bit differently in that we have no prior belief entered into it, right? It's just collect data, look at results. So that posterior distribution, the thing that happens at the end, is a blending of prior belief and results from data, empirical kind of results. And so why that's nice, is that now what we're basically looking at is, instead of science as a one-shot deal with one experiment you're doing right now, or one study you're doing right now, we're allowing previous studies to sort of filter into this analysis. So now it's saying, maybe you find in your study, if you didn't use Bayes, that the mean difference was 2.5, right? Which one do you believe, the 5 or the 2.5? Somewhere you want to probably blend them somewhere, right? So 2.5 should move you off of 5 a little bit, but maybe not all the way to 2.5 or something along those lines, right? And that's what this is trying to do. It's trying to provide the ability to put your prior belief into an analysis itself. That sound cool? Seems a little scary. When you say that, in the world of statistics, Bayes has had a very long history, and it's been very confrontational, maybe? It's somewhat of a point of disagreement in a lot of people, because if you think of an analysis that we've done up to this point in class, there's no prior opinion. It's just data and evidence that come from that analysis. What Bayesian statistics is trying to do is say, well, maybe we bring along some prior opinion with it as well, some prior belief. And yeah, depending on your prior belief, you can really mess with the results of your analysis. Right? You can say, for instance, I might be mischievous, and I might say, well, my prior belief is I think the mean difference is 10, and there's no variance around that. It's just 10. That's it, right? Or variance of 0.1, right? It's really tiny, very tightly peaked. It would take a lot of data to push the posterior away from that prior belief. I'm going to show you that in just a few moments with an example. So if you want to ask what Bayesian statistics is, it's sort of the idea that we can use prior information along with evidence that we've collected to provide a new estimate of what we think the world happens to be. The pros of it is that, yes, we can provide prior belief, and if we do so in a reasonable fashion, it might reflect a little bit more accurate approach to knowledge. The cons are you can really, really play with that prior belief to get a result that you want to see. So that's why in doing Bayesian statistics, it's been very controversial. Some people, up until very recently, it's been like taboo almost in many fields. So, seem weird? Or you're going to say, tell me more, or better yet, if you don't want to hear more, just go ahead and leave. It's been great knowing you. Have a nice summer, right? But no. So here's what happens. To me, though, if I back up a little bit, here's what I like about Bayesian statistics. In Bayes, if you put essentially zero prior belief in, like if you just are agnostic with your belief, like just say basically I have no idea what this mean difference should be, or you put a very conservative difference. Like if your study is to test a mean difference between two groups, and you set the prior mean to 0, like the prior difference to 0, it's very conservative, right? The null result essentially is what you're saying prior belief would be. Or if you set the variance to be very big, you're not doing a whole lot. What happens in the analysis is a couple things. Number one, the analysis proceeds in a way that doesn't essentially allow you to have to rely only on the big sample theory that we've been doing in maximum likelihood. Right, so a lot of our results in maximum likelihood sort of depended on a big sample size to make work. And if you're like many people in the field, I'm guessing Sammy, yourself included, big sample isn't going to happen, right? It'll be hard to do. So Bayes, even without putting too strong of prior beliefs into it, helps you with the idea of what happens in a small sample. So you can have a fairly complicated model with a small sample, and you'll get, to me, what seem to be better estimates of the variability that happens with a small sample. And where that comes from is sort of the lack of reliance on the asymptotics. We're not relying, Bayesian isn't relying on n going to infinity. to make everything become normally distributed. It's allowing you to estimate what that distribution happens to be itself. So I think that's one good thing about it. The other good thing about it is if you're really creative, like I like to think of myself as a really creative guy, and you're kind of like, come on, Templin, you do stats, right? But I express my creativity through statistics, right? Thank you. Ahmed knows this, right? And so the only outlet for that is sometimes you create your own model for the data that makes it. So I hate taking statistics. I hate taking data that you have and then doing stuff to them to make them fit into some prepackaged model or software, right? And so one of the nice things about Bayesian statistics is the estimation packages for it, while they are, again, a little bit of a learning curve to learn, you can pretty much do any type of analysis with them, right? If you've got two outcomes, one of which is a count and one of which is censored, and you have some type of covariance between them, you could build that into an estimation package and do that. I'm saying things that I have no idea how to do, but if you can dream it, you could effectively do it. And that's why I like the other part of Bayesian statistics, is because it's very flexible and it can very easily create things that didn't exist before. So if you have very specific things that are happening in your data, I think you can be truer to your data with them than you would be otherwise. And so I tell you those things as an agnostic. I do not particularly care for prior distributions, and I always ask, and I always have fun with this. If someone says the power of Bayes is the prior, and I'm like, okay, go ahead and pick a homework assignment from this class and set the priors for them. Ooh, right? It's great philosophically, but they have a hard time translating that into actual practice, I feel like. But you don't have to like Bayes. You can take very, very we call them uninformative priors. Priors that don't put a lot of pressure on the data at all, or any, and still get a good result from it. Can I tell you a story? You want to see something? So when I was in grad school, I created a model to do some type of statistics, a psychometric model that hadn't been done before. And sure enough, I don't want that. This model itself used Bayes. And this could be you. This is what I'm saying. Like, you can do pretty much anything with it. Let's do that. Search for patents. My model was I was working with a group at Illinois that would working with ETS externally, and they said, hey, you know what we want to do? We want to patent your model. And so I have on my CV you'll find this one right here. Here. This lists me. That's this guy right here. As a patent, right? So it's like, oh, how's that happen? Well, it turns out if you do Bayesian statistics, again, it was a quick way of getting things done. Let's see if I can show the images for it. But basically, this is part of the world I never knew existed before. But this is what happened, right? ETS is the owner of the patent, and I was listed as inventor. So it's neat that Bayesian statistics is sort of like, I started there. What's wrong with it? I started there. So my grad school experience was, at the end of it, very Bayesian. But it was not Bayesian because I believed in prior information or I wanted to do whatever. It was because there's one example where I had like 36 dimensions to estimate in a latent variable model with categorical data. And maximum likelihood wouldn't do more than like 4 at the time. And so I was able, this is what this is part of. All right, I can do this, put it in Bayes and make it work. So yeah, I'm proud of my patent. There you go. I don't know why, it hasn't brought me $1, but you know. It's just one of those things that you say, hey, I don't know, people claim that I'm not a Bayesian, or I'm trying to give you I have some credibility. Right? I got a patent that does Bayes, doesn't that count? All right? Anyway, yes. So, once again, big picture. Bayes is a way to do really complicated stuff. Shush, I'm sorry. Put that on quiet. Did I tell you the story once in grad school where my stats professor took the phone call? Did I tell you that story? And then he proceeded to order his son a pizza in front of all of us. Right? Yeah. At least I didn't take the call. So, anyway, so why do we want to do this? So here's some, I say 4 main reasons. There's a lot of those. Perhaps you might have missing data. Bayesian statistics is one way you can sort of impute your missing data or use ways of doing missing data in a more or less harmless way of managing what's wrong. Or, this is where I was at, lack of software capable of handling large size analyses. 0 inflated negative binomial with 21 multivariate outcomes with 18 time points? Oh, good luck. All right? I'm saying things that sound complicated, and they are, absolutely. But yeah, where are you going to even start with an estimator for that won't break, right? That's where it goes. What about new models that are out there? Yeah, absolutely. This is creativity. This is like me. I love being creative. Some people do so in poetry or art or literature. I do models, statistical models. But yeah, and then I realize they're not that creative, and I pretty much stink. Or perhaps you're part of this exclusive group I like to call the cult of Bayes. There's sort of people who like believe in Bayes because it's Bayes, and they have like this almost dogmatic religious fervor to them. I don't know if you've ever seen that before. You know that have you met anybody who's has to do Bayes? I've seen some smiles. Nobody. As you go on, you may encounter some of them. And I don't think less of them as people. That's just their philosophy. It's just people are like, oh no, they believe that some very big philosophical differences exist between the analysis. And it's true, there are some philosophical differences between it. But as n goes to infinity, the differences start to go away, and it's sort of this odd mix. You're sort of in a spot where asymptotics haven't fit in, is where they live. So, and I'm cool with that. That's fine. There are some differences with it, quantifiable differences, but that's it. So, questions, comments? Yeah, Ryan.
This might sound really dumb.
Not at all.
When you say that you can make a new model,
Mm-hmm.
what do you like?
So literally, the way I look at statistical models is through it's like there's certain kind of tenets that hold things together in statistics, and you sort of learn a little bit about it. But basically, you want to create a model that does something nonlinear or has an effect that you haven't quantified before. Or better yet, like for me, my model I wanted was I had this, instead of taking a kind of a factor analysis where you have a continuous factor, I had a factor that had 2 groups, a high group and a low group. And I needed to put it into software somewhere. And so there are ways of doing that. The other part to it is if you've got data that don't quite behave normally, like a normal distribution, or don't quite behave as a categorical distribution, or you have an idea on how missing data should be, there's all sorts of nuances that just don't show up in packaged software. This is a way to solve that. So, other questions, thoughts? That's why that's kind of the motivation for the patent. Is like this is a new model that nobody tried yet, and so, and honestly, nobody's tried since. So while I say, yeah, I got a patent, yeah, babe, but nobody used it. Bingo. Probably no one should ever use it. So that's how you know. That's how you know to be very. I mean, I like to argue with people, but at the same time, I'm trying to keep a healthy. I'm wrong a lot, right? It's good to be wrong a lot. So whenever you get to cite your own dissertation and say that the author was wrong, I've had to do that before. That's fun, isn't it? Right? So I hope that I tell you that in a couple of reasons, not to fear your dissertation, but to make it more real. Like it's just another task. It's the last hoop you have to jump through in academics. Hopefully. So, the use of Bayesian statistics have been controversial. So this is sort of a perception of it. And in many different fields, this is still controversial. It's very hard to get papers published if a lot of people in your field do not use Bayes, because the implication that a lot of people have is it's cheating. You have a prior distribution. You're putting your prior belief on the analysis, and I don't know to what extent the prior belief actually is informing the analysis. But there are ways in documenting your results where you can show, yeah, it's really not informing it a lot. I think you can kind of do it, what we call a sensitivity analysis. The other part that is difficult is that if you thought using like NLME was hard, the Bayes packages are pretty hard too, right? Depending on what you use, and they're getting better and better, but the other part to it is that they take a long time to run. There's a part of the syntax I gave you at the end where I took Lavon, where most of us enjoyed Lavon, I think. Would you say between Lavon and NLME, would you pick Lavon? How many would pick Lavon over it? How many pick NLME? All right, 0, right? Well, I have a former grad school colleague for a year and professor who's at Missouri. He has a package called Blavon, which is Bayesian Lavon. And it's the same syntax. It just calls out to JAGs, and it does stuff. And so I have an example for you in the slides. But if you were to run that, it'd take probably 20 minutes, maybe 15. And it's one of the analyses I use with path analysis example that took seconds the other way. So it takes a long time to run these models. So until very recently, there are very few models available unless you're really adept at low-level computer languages like C or Fortran or C++. So you can see so you're telling me it's controversial, I may not get it published already, and it's going to take forever to do? Where do I sign up? And that was me. That was me in grad school. That's right. Well, that was me. That's actually been me in life. Like whenever I was like a student in elementary school, like you need to hear my life story, but I'll tell you it anyway. A student in elementary school, everybody did that was back when they supported like band or stuff in elementary school, and like they're like, all right, you want to participate? Like, sure, why not? And they're like, okay, well, everybody's doing band. I'm like, well, I'll do orchestra. I'll do the strings. And the strings, everybody's doing violin. Oh, what's nobody doing? Cello. I'll take that one, right? So that's me. I always try to go that way. I don't know why, but just to be different, I guess. So what's cool about this, in some respects, though, is that where Bayes started actually happened a lot before what we usually use right now in statistics in general. So the Bayes theorem that it's based on, Thomas Bayes, this was in the 1700s, where a lot of the stuff that we hold on to now it came from like statistics work in the 1930s. We're talking 150, 160 years ahead of Fisher, right? That's a pretty big deal. However, because things were so difficult to derive and so difficult to do computationally, and because we didn't have a computer up until recently, you didn't see a lot of Bayes. It was really stuck in places that we didn't think about, particularly in education, certainly in the social sciences as well. But in the last 20 years, 30 years, things have gotten much, much better in statistics. And then as we get into social sciences as well, things are much better. We got better at estimating it. We actually took algorithms that started in chemistry, physics, and we're using those. And so people crossed fields and made things work. So it's kind of fun. It's one of the few times I can go into a room with a bunch of hard scientists. I do a lot of Bayes stuff, and so I need a lot of computing equipment. And so when you go into the room with the people who are the biologists or the physicists or the chemists or the engineers, I'm in education. And they sort of chuckle. I'm like, well, and then I start describing what I'm doing, and then they get really quiet. Okay, that's cool. Okay, yeah, it happens all over the place, right? So it's kind of neat to see. Let's talk about how they work. Oh, any other questions real quick? That's kind of the big picture. They're hard to use, relatively speaking. They're getting easier. A lot of people are really liking them a lot faster now. My guess is in the next 10 years, almost everything is going to be some version of Bayes, I think, as we come out. Maybe not 10 years, but Bayes is becoming pretty mainstream these days. So it's just a matter of time before it becomes mainstream in your world too. So how do they work? Bayes, the term Bayes refers to Thomas Bayes, who was some type of monk or religious figure of some sort. Maybe you know better than me. Bless you. And so this dude created Bayes' theorem, and that's Bayes' theorem up on the screen there. I don't need to get into the specifics of it, but when you took your first stats class, there's usually some type of Bayes topic that comes up with this somewhere, usually a contingency table, right? But what's involved in this often is if you want the probability of an event A conditional on something B, what goes into that is the probability of B given A times the prior probability of A. So that thing right there is going to become our prior. And that thing right over on this part right over here, B given A, is our likelihood of the data given our parameters themselves. So here's the example that here's an example that is similar to ones that I remember taking in my very first statistics class. Imagine a patient takes a test for a rare disease. Now, this disease is so rare that it only happens in 1% of a population. That test has a 95% accuracy rate. Right? So what is the probability that the patient actually has the disease? Right? If the test comes back positive, what's the probability the patient actually has the disease? Well, let's go and define a couple things. I probably worded that really badly, but so here we're going to say D is the case where the person actually has the disease, and ND is the case where a person does not have the disease, and a plus is the time where a person's disease is a test for the disease is positive. So the question is asking for the probability a person has the disease, or D, given that the test came back positive. So formulating that in Bayes' theorem, what we're after is the probability, what we need to do to calculate this, we need to know the probability that someone tests positive given that they have the disease times the prior probability of the disease itself. So we knew that the prior probability, there's 1% chance a person in the population has the disease. And my terrible wording, the 95% accuracy rate really meant conditional on the fact that a person has the disease, the probability of the test being positive turns out to be 0.95, right? So what we can do, now we know all the little parts that go into this equation. If we calculate all this out, what we can see is that disease, maybe, there we go. We'll plug all of this in. Actually, this part right here, this bottom part, we don't know the probability of a positive test overall, but that comes from this sum right here, which I won't need to get into too much. But what we can show is the probability that a person has the disease given that the test is positive actually turns out to be only 17%, 0.17. And that's where Bayes' theorem is really taking data into consideration. Right? It's saying, okay, the disease has this amount of accuracy, right? So basically, the proportion of time or percent of times that a test would come back positive if you actually had the disease. And we also know the prior probability that someone in the population has these. It's a really rare event. 1% of the population has it. So when we put all that together, we see that this actually turns out to be a very small number. The probability that somebody has the disease is 0.17. Weird, right? Yeah. Did you see problems like this in any of your stats life? Anybody? Some did. But if you haven't, that's sort of what the process goes. Although not everything is as clear-cut as these categorical distributions, here is a more relevant example. Using a linear model. You like linear models? Or you put up with them? Sort of runs the world. Imagine you administered an IQ test to a sample of 50 people, right? And so you say Y is person P's IQ test score. And if we were to put this into a linear models context, we could say there's an empty model, right? Y is equal to beta 0 plus error. And we know before beta 0 turns out to be the mean of Y. And error has a variance that goes around it as well. All right, so from this empty model, we know beta 0 is the mean of Y. Sigma squared is the variance of Y. And the conditional distribution of Y is, or Y given beta 0 and sigma squared, is this right here. We say that Y comes from a normal distribution for the mean of beta 0 and a variance of sigma squared error. Right? This is stuff I've talked about blah, blah, blah the whole time in class. Too much math, too many symbols. But we can do this in ML and REML. This is our likelihood function. Remember the ML part of the class. And here, using the GLS package, I found beta 0 to be 102. And actually, this is where I can flip over to R here. But here is my data. And here's what I have. I have beta 0 being 102.769. And here is, I had a standard error of 15.63, so that thing squared is 239.49. And the log likelihood is negative 207.91. Right? This is just what we would do with a typical maximum likelihood analysis, right? Seem somewhat familiar? Let's put this in a Bayes context. So the Bayes approach needs a prior distribution. And so we're going to say, let's create a prior distribution for each of these parameters. We have two parameters in the model. We've got an intercept, which happens to be the mean of y, and we've got a variance, which happens to be the variance of y as well. And I'm just going to do this to show you how priors work on the analysis itself. Right? This is nothing. This is not going to be all that groundbreaking stuff, but I want to show you how it works. So we're coming up on our break in a couple minutes, but let's just talk about priors real quick. Let's imagine that you've been told that that this version of the IQ test is supposed to have a mean of 100 and a standard deviation of 15. Right? That's like saying beta 0 should be 100, and sigma squared should be 15 squared, or 225. Right? That's sort of the prior that you're looking at here. That's sort of anchoring where the prior should be. And so maybe you've gone and found results from administering various administrations of this test and found that the sampling distribution of the mean had a standard deviation of 2.13. You could say that the prior distribution might follow a normal distribution with a mean of 100 and a variance of 2.13 squared, right? Using that prior information you may have had. Now, if you don't have that information, hang on. I've got an example here where we're like, no, let's play around with it. Let's make it different. We can see what different priors do with this. Let's also go with the variance. Variance, by the way, is really hard to find. I've always found it to be very difficult to get a prior for because the sampling distribution of the variance is a nightmare. But let's imagine you think the variance should be somewhere between 200 and 400. Why not? So we're going to use a uniform distribution as prior for that. Bless you. Between 200 and 400 is where it goes. Right? And so that's basically saying, I have no idea where that variance should be, with the exception of between 200 and 400. It can't be outside of that range, but somewhere between there is 200 and 400. Now, how do you feel about these priors? Before we take our break, how do you feel about these priors? Does it worry you at all that we might be biasing our results? It should be, because that's the choice of prior will always influence the results. Particularly this variance one. That's a very narrow range of variance. I'm thinking of all the things it could be, right? So let's take a break now, and in 10 minutes, let's come back, and we can see what happens with this, all right? All right. Thank you.